In today's lecture, we shall be considering non-parametric tests. This lecture introduces non-parametric tests, which are distribution-free methods suitable for categorical and ordinal data. We shall focus on the chi-square test family, explaining the uncorrected chi-square test for association between categorical variables, including step-by-step calculations and worked examples. We will also cover specialized variations of the chi-square test, and these include the Yates corrected chi-square test, which we use when we have small expected frequencies, the Mantel-Haenszel chi-square test, which we use when we seek to control for variables through stratification. The McNemar chi-square is used for paired categorical data, while we use the Fisher's exact test for very small samples. Each of these methods is illustrated with practical examples from medical research, emphasizing when each test is appropriate and how to interpret results correctly. Statistical tests can be grouped into two: parametric and non-parametric. The parametric tests are applicable to variables that assume a normal distribution in the population of study. The non-parametric tests are called distribution-free because they do not make this assumption of normal distribution, and they are applicable to categorical and ordinal variables. What are the types of non-parametric tests we commonly encounter? We have the chi-square tests, which include the Yates corrected chi-square test, the Mantel-Haenszel chi-square, the McNemar chi-square, and the Fisher exact. We also have the Kruskal-Wallis test, which is the non-parametric version of the ANOVA test, and of course, the logistic regression, which we have encountered commonly and often used, is also a type of non-parametric test. The uncorrected chi-square test is the most commonly used non-parametric test. It's usually used to look for association between different categories. In this instance, both the independent and dependent variables are categorical variables, and this tells us when to use the chi-square test. We use the chi-square test when both the independent and dependent variables are categorical. The chi-square test is based on measuring the difference between observed frequencies and expected frequencies. If the null hypothesis is true, there should be no difference in the observed and expected frequencies in the groups being compared. What are the steps to performing the test? The very first step is to decide on the level of significance, and we usually refer to this as our p-value. That is our alpha level. That is the level or probability of committing a type 1 error. We usually set this at 5%, or in some cases we may go with 1%. We then calculate the chi-square statistic, and then we look at this chi-square table to find the critical value, and then we interpret the result and make a decision. So these are the 4 steps in performing the test. So, in calculating the expected frequency, we take the product of the row total and the column total and divide by the overall total. And then from each cell, we subtract the expected frequency from the observed frequency and square the result, and then divide by the expected frequency. And then we add up the results of the above calculations for all the cells in order to get a value for chi-square. Thus, the chi-square test is the sum of the observed minus the expected frequency squared divided by the expected frequency for all the cells. We next determine the degrees of freedom, which is given to us by the number of rows minus 1 times the number of columns minus 1. And then we check the chi-square value in the chi-square table using the agreed p-value and the degree of freedom. We then interpret the result by comparing the calculated chi-square value with the chi-square value from the chi-square table. If the calculated value is higher than the value from the table, then we can say the p-value is less than what has been set, and the observed difference is set to be significant. So here's a worked example. Suppose that in a study of the factors affecting the utilization of antenatal clinics, we found that 64% of 80 women who lived within 10 kilometers of a clinic came for antenatal care, compared to only 47% of 75 women who lived more than 10 kilometers away. At face value, this would suggest that antenatal care is used much more often by women who live close to the clinics. But the question is whether this difference in utilization is significant. So if we look at our contingency table, we find that 51 out of 80 women living within 10 kilometers of the antenatal care used the antenatal care facility, compared to 35 out of 75 women who lived more than 10 kilometers or more away. Of course, the second table shows the calculated expected frequencies. Remember how the expected frequencies are calculated? So it's the product of the row total and the column total divided by the grand total. So and we see it. We calculate the chi-squared statistic by adding up all the expected frequencies. All what we've gotten. The observed minus the expected frequency squared over the expected frequency. We do that for all the cells. And this gives us a chi-squared statistic of 4.55. So the next question is, how does this compare to the critical value? In determining the degree of freedom, we have a degree of freedom of 1, which we got by the number of rows minus 1 times the number of columns minus 1. And so we have 2 rows, 2 columns, and so that becomes 1 times 1, gives us a degree of freedom of 1. We look up the value of the theoretical chi-square test on the table and compare with the calculated chi-square statistic and identify the chi-square with the biggest value. Now the chi-square value or critical value at degree of freedom equals to 1 and a p of 0.05 is 3.84. So let's think about it. So we calculated our chi-square statistic of 4.55 and we have the critical value at degrees of freedom 1 and p equals 0.05 of 3.84. So what is the interpretation of our result? Because the calculated chi-square test, or rather statistic of 4.55 is larger than the critical value of 3.84 from the chi-square table, this means that the p-value is less than 0.05. So women living within a distance of 10 kilometers from the clinic use antenatal care significantly more often than women living more than 10 kilometers away. Remember, what does the p-value mean? What it means, if you recall earlier lectures, is that it's the probability of observing this data or data that is more extreme than this if the null hypothesis were true. And so we see this in how we interpret the statistics. Your calculated chi-square test is 4.55. This is larger than 3.84. So it means the probability of observing this particular data is, if the null value were true, is probably not happenstance or not by chance. And so that's why we're able to say the p-value is less than 0.05. Here is a shortcut formula for calculating the chi-square test. We really don't need to go through all that observed minus expected all squared over divided by expected and then summing up. The chi-square test can actually be calculated by plugging in the values from the cells of this 2x2 contingency table into this formula. Of course, this formula only holds true for 2x2 tables. Where you begin to have more than 2 rows or 2 columns, we can't use this formula. But if you have a 2 by 2 table, you can use this as a quick shortcut to calculate the chi-square statistic. What about the Yates corrected chi-square test? When do we use it? Suppose we study mortality in malaria and we get the following results. Survival for chloroquine versus quinine is 96.2% versus 92.6%. Is this difference significant? So if we have a 2 by 2 contingency table, and so those who took quinine, 75 of 78 of them survived, or rather those who took chloroquine, 75 of 78 of them survived, and those who took quinine, 75 of 81 of them survived. The second table gives us the expected frequencies. The uncorrected chi-square test gives us 0.944. This is less than the critical value of 3.84 at 1 degree of freedom and p 0.05. So what this tells us is that the p-value is greater than 0.05. But we have a problem here. And what is that problem? The expected values in the chloroquine and quinine dyed cells are both less than 5. You can see that 4.4 and 4.6. So we have expected cell values that are less than 5. The general rule is that the chi-square test is not valid when an expected value is less than 5. However, you can use the Yates correction in a 2 by 2 table to partially compensate for low expected values in cells, as long as most of the cells have expected values greater than 5. So this is the caveat. If most of the cells have expected values greater than 5, then we can use the Yates correction to partially compensate for low expected values. And so to make the correction, we make a slight change to the formula we use for calculating expected frequencies. We add 0.5 to the numerator 10 so that it becomes observed frequencies minus expected frequency plus 0.5 and then square. So for example, in the chloroquine dyed cell above, we would use 3 minus 4.4 plus 0.5 all squared divided by 4.4 and so on. By the time we do that, we find that we have applied the Yates correction. So here is the formula, again, similar to the first one, for a 2 by 2 table to apply the Yates correction. We use the Mantel-Haenszel chi-square test to deal with confounding. And here is a worked example. Supposing that in a survey of schistosomiasis in 2 villages, A and B, the research obtained the following results. So we have village A and village B. And the hypothesis being tested here is whether the prevalence of schistosomiasis in both villages is different. And so the uncorrected chi-square test gives us a value of 0.009 with a p-value greater than 0.05. So at face value, we are unable to reject the null hypothesis. Both villages seem to have the same prevalence of 32%. However, even though the prevalence is the same in both villages, we suspect that the age may be a confounding variable. And so the investigator decides to break the table into 2 by stratifying on age. So we stratify on age 5 to 19 years versus age 20 years and above. And when we do that, we have 2 different tables now. We have the table that includes children aged 5 to 19 years, in which case we find that 37 out of 60 children in village A have schistosomiasis, compared to 73 out of 190 children in village B. If we look at adults 20 years and above, we find a different distribution. Calculating the chi-square separately for these two different tables, we find that there is a statistically significant difference in prevalence between village A and B when we look at children 5 years to 19 years of age. Whereas among adults 20 years and above, there is really no difference between the two villages. This is a classic example of confounding. So how do we use the Mantel-Haenszel test to deal with confounding? We do that by breaking the data down according to the confounding variable. So we stratify. And after stratifying, we apply the Mantel-Haenszel chi-square test. The prevalence of schistosomiasis in children was statistically significantly different from the prevalence in adults. And that's what we saw. There are more children in village B, and schistosomiasis is more common in children in village A than B. So age in this case is a confounding variable because it affects the variable of interest, which is the prevalence of schistosomiasis and the groups being compared, residents in villages A or B. What about when there is pairing of the data? What do we do? In this instance, we use the McNemar chi-squared test. In dealing with paired observations that are categorical, we cannot use the usual chi-square test and we cannot use the Mantel-Haenszel test. These are not appropriate. The appropriate test to use is the McNemar's chi-square test, which we use for nominal data to compare proportions of paired observations. So as an example, in an outbreak of cholera in a community, a study was conducted to identify the causes of the cholera. So for each cholera case, a subject was sought of the same age decade, sex, and the same neighborhood. So in other words, we matched the cases with suitable controls. We matched them on age, on gender, and residence. Each case and its control are treated as a pair, and the information obtained on seafood consumption by each case and control is a pair. So if you look at the contingency table, this is how we represent the data for paired categorical variables. So we have cases, we have controls. And then the question is whether they ate seafood or not. So what we do is we find the cells where there is discordance. So we can see for cases who did not eat seafood with corresponding controls that ate seafood, there are 3 people in that cell. There are 3 people in that cell. For cases who ate seafood with corresponding controls who did not eat seafood, we have 30 individuals. So these cells are discordant cells. So 12 pairs of both cases and control ate seafood. 31 pairs did not eat seafood. These pairs, which are concordant, do not give us information about whether eating seafood is a risk factor for getting cholera. In 30 pairs, the cases ate seafood, but the control did not. And in 3 pairs, cases did not eat seafood, but the control did. It would therefore appear to us that eating seafood is a risk factor for getting cholera. This assumption is only true provided that the McNemar chi-square test gives a significant result. And this is how we calculate the chi-square test. We should use the McNemar test only when the number of discordant pairs is 20 or more. Another way of handling small expected values in 2x2 tables is to use the Fisher exact test. This uses probability theory to calculate the exact probability of obtaining the observed or greater departure from the expected. This test is suitable for sample sizes less than 40, where chi-square test is not recommended. The test treats data in a manner similar to the chi-square test. And so oftentimes when you do your statistical analysis, within the software output, you will find that it will produce a range of all these results in the report. So you're going to see the chi-square test, you're going to see the uncorrected chi-square test, the Yates corrected test, the Fisher exact test. Which one you choose to report will depend on taking a look at your contingency tables and looking at what the expected values are. Oftentimes, the statistical software will provide a warning when expected cell values are less than 5. Again, this is just for us to be aware. Not expecting any of us here to memorize or manually calculate the Fisher exact test. Having considered all this, we must bear in mind that the use of statistical tests for signal testing has been made simple through the use of computers. What we need to know is how to give the appropriate command. And once the computer has done the analysis, we must know what to look for to be able to make the right interpretation. And this is what this course is about, to provide us with the tools we need to be able to look at that output and make the right conclusions and interpretations.